Alright everyone, my name is Dr. Sunny Goh Eng Kiap. I'm from the Faculty of Ocean Engineering, Technology and Informatics. So today's lecture, I would like to talk about soil solid phase. Soil solid phase. Soil itself has solid, liquid, gases and living organisms. The plant grow on it. The soil itself, it holds water, nutrient and oxygen for plant root. So soil solid phase can be broadly divided into two parts, the mineral parts and also the organic matter part. The mineral part, we have particles with different sizes, shapes and chemical composition. And the sizes of the mineral ranging from colloidal to coarse like sand and gravel. The organic metals include the organisms, plant, animal residue at different stages of decomposition. Basically, it means in the soil there are minerals and also organic metals. The organic metals are going through the process of degradation. In the soil, there is an empty space between soil particles. So the soil itself can be fully or partially filled with water that contain many different chemicals. So when we pour water into the soil, the water is being pulled down by gravity, and some of the water will attract to the solid surface of the soil. So when the soil is empty, it's lack of water, so the space in the soil particles is filled up by gas. So the gas fill empty space that's not filled by water. Solid phase has a dominant influence on heat, water, and chemical transport and retention processes. So here are the figures showing different stages of soil moisture. For example, we can look at picture A. So picture A shows that the soil is actually a moist soil. A moist soils, we have not only the inorganic particles, which is the mineral, and also the organic metals, and there is a spaces where we have a pore space and also gas phase. But at the same time, since this is a moist soil, we have a liquid that fill parts of the soil. And the B part, if you look at the soil, soil saturated with water, so you can see that the soil is apart from organic and inorganic metals, we don't have pore space, because the pore space is filled up by liquid. The liquid itself is the water. All right, and if you look at the figure 3, this is a completely dry soil. So a completely dry soil, we only have organic and inorganic particle, but then the spaces between the organic and inorganic particles, it is completely dry, so we only have pore space and organic and inorganic particles. So in this case, we have no liquid but only gases. All right, in picture 3. So if you look at the diagram here on the right side, you can see that there's a difference between non-compacted soil and a compacted soil. In a non-compacted soil, you have a loose particles that is loosely arranged, and in this situation, we have soil particles, and which is also attached by liquid water, but it is loosely arranged. But if you look at the compacted soil, you have you have soil particles attached with water. At the same time, it is more well arranged or more closely arranged with each other. So the two figure is the same. The only difference is that one is non-compacted while the other one is compacted. The one that is compacted will have less space for air. The one that is non-compacted, you have more space for air. So we can divide the soil volume into 3 compartments: the soil particle itself, the water itself, and the gas itself. So you have the volume for soil solid particles. You have the volume for water. You also have the volume for air. So the volume for solid is Vs, the volume for water is Vw, and the volume for air is Va. So if you sum VA, VW, and VS, you will get V as in total. So you can see that soil particle constitute a larger volume than the volume constituted by water, and then of course the least volume is given by gas. Now we can talk about the characterizations of particle size. We use sheaf and sedimentation. So first, the soil need to be pre-treated with hydrogen sulfide to remove organic material. And we have to disperse the aggregate. Sometimes the soil is very sticky, they stick together like a lump, like a cementation. So we use Calgon solution to remove the aggregate. We also use HCl to remove the calcium carbonate, which causes the cementation. So in this case, we disintegrate the cement. And we pass through the liquid that after subjected to hydrogen sulfide and Calgon solution and HCl, we pass the liquid through the core screen. The core screen size is 0.05 mm or 50 micrometer. And the particle left on top is actually the sand. And the liquid passing through the screen is then characterized using hydrometer method or pipette method. And the pipette method itself or hydrometer method itself will help us to determine the clay content so that we can know the silt content. Because we know that the silt plus clay plus sand gives us 100%. So if we can determine sand and clay, therefore we can determine the silt content. So below here is the equation that used to determine the speed of sedimentation. So this is only for your information. So the equation relates the particle diameters with particle velocity. So if any of you are interested to know more, please let me know, we can talk more about it. Okay, let's talk about classifications of textural size fraction. There are basically two standards, the USDA standard or the ISSS standard. So in this case, we should refer to the USDA standard that is widely used. Okay, so we are only in soil physics. We are only interested in sand, silt, and clay in terms of mass fraction. So it's good to know that clay. When you talk about clay, you should talk about the size that is less than 0.002 millimeter. When you talk about silt, you talk about the size between 0.05 millimeter to 0.002 millimeter. When you talk about sand, you talk about the size between 2 millimeter to 0.05 millimeter. Okay, clay has more influence on the physical and chemical process of in the soil than sand and silt. This is because a large surface area of clay and its reactive surface area. So imagine that just now we talk about the sand, silt, and clay. So you can see that clay has a very small size. So when the clay has a very small size, the smaller the size of the particle, the greater the surface area. So when we have a greater surface area, we have more surface area actually come in contact with the liquid water. So if, for example, the liquid water has pollution, the pollution, for example, heavy metals, stuff like that, they are carried by water as they come in contact with the surface area of clay. So it will attach to the surface area of clay because clay has more surface area compared to sand and silt. Clay has more surface area because the size is small. All right. So that's why they call it. They have more reactive surface area. In fact, sand and silt also has reactive surface area. It's just that the clay surface area, it has more surface area for absorption and desorption process to take place. And sand and silt are passive entity because they have less surface area, and their influence on soil water depends on geometric arrangement of particles. Sandy soil do not retain water significantly and require frequent water addition to avoid plant stress. Sandy soil, basically they have a greater pore space between particles. As a result, water can be easily flow through the soil due to the influence of gravity, and only a portions of water actually attached to the surface of the sandy soil. As a result, this sandy soil cannot retain a lot of water. Because of that, we need to give more water into we have to provide more water to sandy soil. So here is exercise 1. Take for example a soil with 60% of silt and 60% of silt and then 20% of sand. So you can determine the types of texture, which is the silt loam. So whatever things that fall between this area, it is a silt loam. So since this dot falls within the silt loam area, so we call this soil as a silt loam. And because 60% plus 20%, we know that another 20% here is given by clay. So this soil is called silt loam. Okay, exercise 2. A soil with 30% of silt, 30% of silt, all right, and 10% of sand. So you can estimate that the point of connection is actually within the area of clay. So this clay, this is a clay soil. So we have a 30% plus 10%. We have another 60% left. The 60% is actually clay, and this soil texture is clay soil. Okay, let's look at example 3. So here we have 10% of clay. Okay, 10% of clay, 60% of sand. Then you know the point of connection actually falls within the sandy loam area. So this is a sandy loam. You have around 30% of silt. So this is a sandy loam soil. All right. So soil physics properties are sensitive to distributions of particles and pore sizes. All right. Hence, it is useful to construct mass fractions of soil particle as a function of effective particles diameter, which is known as particle size distribution. So this diagram here is show to you the plot of particle diameters versus the cumulative mass fraction. All right. So the mass fraction in the end you will get 100%. So 1.0 is actually referring to 100%, and the particle diameter is actually referring to the size of the sheaf. Okay, the size of sheaf that used to sheaf this the soil. So you have a royal silt loam, Palos silt loam, Salcombe silt loam, and red bluff clay. So these are different types of soil texture, right? From different place. Yeah, we talk about shiver. Yeah, so this is the shiver that used to shift the soil into different sizes, and from there we can actually determine determine the particle size distribution. Okay, so now you can see that at 50% of cumulative mass fraction, you see that those with clay, it has smaller size of particles compared with silt loam, which has a larger size. So I think it is common because as we know that clay, this is correct because we know that clay has a smaller size. All right. And a different abundance, which means the mass of particles of given diameter as shown in figure 1.2. Okay. So shape of soil particle. Soil concept model assume individual soil particles as spherical in shape. From experimental evidence, soil particles are non-spherical. So for example, just now we talked about silt, clay, and sand. So the clay looks like plate-like and dish shape. So you see that this is exactly the clay looks like when you look under the microscope. Okay. And the surface area of soil particles, when we talk about surface area, we talk about specific surface. Specific surface referring to is referring to surface area per mass. All right. So a large S means a large specific surface, means that a large reactive surface. Soil organic fraction has a high reactive surface. that may have property characteristic of material with an extremely high specific surface area. For example, organic matter has 1000 meters square per gram. So that is very large surface area. Organic and clay fraction have a significant influence on the surface area of soil. Alright, here's the table 1.1, shows a specific surface area S of idealized shapes representing prototype particles found in soil. So we can see that the effective diameter for gravel is actually bigger, and the smallest one is given by clay. And then when we try to calculate the specific surface area, you can see that the clay is actually higher, the highest in the specific surface area compared to silt, sand, and gravel. So let's talk about volume fractions. So as I mentioned to you before, in the soil you can break it down into the volume given by solid, the volume given by water in the soil, and the volume given by the air in the soil. So we normally can see that solid takes the highest volume, followed by water and air. So the volume take up by solid, we call it Vs or V solid. The volume take up by water, we call it Vw or V water, and the volume take up by air, we call it Va or V air. All right. So the total is called V soil. All right, and the V air plus V water, we normally lump it together. We call it V pore. Okay, V pore mean pore space or empty or the space between the soil particles. So you can see that soil volume or Vt is given by Va plus Vl. Vl is actually the liquid, Va is the air, Vs is the solid. So A is gas phase, L is liquid phase, and S is solid phase. And then if we divide this equation by Vt, by V total, so we will get 1 equals to theta A, theta L plus theta S. Okay, so theta A is given by Va divided by Vt. Theta L is given by Vl over Vt, and theta S is given by Vs over Vt. Alright, so if we can lump together, we can sum together theta A, the air space, with theta L, the liquid space, then we will form a phi, a coefficient called phi. This phi is what we call porosity. Okay, porosity. So in this case, we can simplify this equation into 1 equals to phi, the porosity, which is equals to the sum of theta A plus theta L, and then of course here we can phi plus theta S. So theta S is a solid. All right. So we can rearrange this equation. So we get the porosity equals to 1 minus theta S. So phi is called porosity. It's a meter cube over meter cube. Theta A is volumetric air content, meter cube over meter cube. And theta L is volumetric water content, meter cube over meter cube. And theta S is volumetric solid content, also meter cube over meter cube. Okay, so now let's talk about bulk density. So when we try to characterize the soil, one of the important parameters is the bulk density. So bulk density is basically defined as the mass of the dry soil per volume of soil. So we take the dry mass of the soil divided by the total volume of the soil. So let's say this is a cylinder, empty cylinder, we hammer it down into the soil, and then we remove the volume, the volume of the cylinder that contain the soil. So the volume inside the cylinder is the Vt, okay, total volume. All right, and then we take this soil, we dry it, and then we can know the dry soil. So we can get the Ms. So we take Ms divided by Vt, the total volume of the soil, and we get the bulk density. So, and then there's another parameter called particle density. Particle density is defined as the mass of dry soil per volume of soil solid. Okay, so we can actually relate bulk density with the particle density. Okay, so what's the difference between Vt and Vs? As you know, Vt include the air space and the space occupied by water, and also the solid volume, right? But Vs is only the solid volume, excluding the space given by the air, and also excluding the space given by the water. So you remember the previous slide. So Vt equals to Va plus Vl plus Vs, right? So Vt is including air, liquid, and solid. So Vt including the air, liquid, and solid. Okay, and Vs is only the solid particle volume. Okay, so now we can write out the equation for bulk density. So bulk density is equals to ms over Vt. Okay, Vt. So we get ms over Vt. We can rearrange. We can break ms over Vt into two parts, and then we add Vs at the top of Vt, and then we add Vs at the bottom of ms. So we can have two different ratio here. All right, and then the ms over Vs, as you know, ms over Vs is actually representing the particle density. Okay, so ms over Vs, we can now write it as rho as the particle density, and then the Vs over Vt, as you know, the Vs over Vt is actually the volume volumetric soil content. So as you see in the previous slide, theta s is a volumetric solid content. Okay, theta s is given by, where is the theta s? Okay, theta s is given by Vs over Vt. So this is a Vs over Vt, so it's a theta s. All right, so as you know that theta s in it, theta s can also be written as 1 minus phi. Okay, so you move the theta s here and the phi over here, so it becomes theta s equals to 1 minus phi. So we can write theta s equals to 1 minus phi. So now the rho b is equals to rho s in bracket 1 minus phi. Okay, and you know that phi is actually the constituent, is a sum of phi is a sum of what? Phi is a sum of theta a plus theta l. So now you can get 1 minus theta a minus theta l. So this is a formula being derived to show you that how the soil parameters are being related to one another. And don't worry about the derivation of this equation. When it's needed in the exam, this formula will be given to you. All right. So bulk density measurement. So to measure bulk density, a soil core sample is taken, right, as shown in this picture. Okay, so we take a cylinder, we hammer it down into the soil to take the soil sample. So a core soil sample is taken and dried for 24 hours at 105 degrees Celsius, and its dry mass is weighted. Okay, so we get the ms, and then the volume Vt is a volume of the cylinder. Okay, volume of the inner cylinder. Okay, so volume Vt is assumed to be part of that sampling tube. Okay, so the bulk density is equals to the dry mass over the volume of the sampling tube. Okay, or the volume of the cylinder. All right, that's the end. Thank you very much.